or it's going to compare difference of squares to perfect square trinomial and also show you how to recognize a perfect square trinomial rather quickly. So I'll use the initials PST and then I'll use the initials DOS. So just to quickly point out the difference between the two patterns, these are the two patterns with the quadratics or polynomials. Notice that the difference of squares, the binomial factors are almost the same. One operation is addition, the other operation is subtraction. So that when you take this product, you're simply left with two perfect squares connected by subtraction, which is why it's called a difference of squares. Comparing that to the other pattern, the perfect square trinomial, this is the same binomial times itself. So you're forced to have that linear term, the term in the middle. So if I were to take the product with the first pair, and I'll do a few of these and then we'll stop and compare for just a minute. And let's see, let me do this. And then on the last example, I need to combine like terms. So this is going to clean up to look like 48x in the middle and there. So let's analyze the three products that I've taken. I'll box them in red. So notice that each product begins and ends with a perfect square. And notice that the constant, the last term, is a positive perfect square. So I've got a perfect square ending with a perfect square, and the third example, a perfect square ending with a perfect square. So when you take the binomial and you multiply the binomial times itself, it generates what's called the perfect square trinomial. Three terms, with the first and the third term being perfect squares, and the first and the third term also being positive numbers. So I want to teach you how to recognize this when you see the end result trinomial, how to work in the reverse to recognize the pattern. So let's move down to the solve portion. So down here, I have some that have already been multiplied together, and I would like to show you how to recognize or untangle the pattern rather quickly. So here I'm going to do a little mental check. I have a perfect square and a perfect square, noting that they're both positive. So if this is in fact my pattern, it's implied that I'm going to have the same binomial multiplied times itself. If I take the square root of 25x squared, that's going to be 5x. If I take the square root of 144, that is 12. I notice that the term in the middle is addition, so that means that the operation inside the binomial factor is also going to be addition. I also need to check to make sure that 120 would be generated if I were to multiply this binomial times itself. So a quick way to do that is to multiply 5 times 12, and that generates 60. Is the term in the middle 60 plus 60, or 120? If it is, then 5x plus 12 squared, or 5x plus 12 times itself, would be the factored form of the trinomial that's presented. And then in the world of solving, you would just simply take the factor of 5x plus 12, set it equal to 0, and you would have 1 root of negative 12 over 5. So with this pattern, you only have 1 root. So the binomial times itself would just generate 1 root or 1 solution. Let's do the second example presented on the screen. So mentally checking, beginning and ending with positive perfect squares. So if this is the pattern, it's going to be the same binomial times itself. The square root of 49x squared is 7x. The square root of 169 is 13. The operation in the middle is negative, or is subtraction, so that means that the binomial factor would have a negative sign in the middle. 7 times 13 is 91. 7 times 13 is 91. 7 times 13, 7x times 13 generates 91x. Is the term in the middle 91x plus 2, or 91x times 2 rather? And it is. That does generate 182x. So that means that this is the pattern, and the factored form of that pattern would be 7x minus 13 squared. If I were to solve this, I would just simply take 7x minus 13, set it equal to 0. I would would have 1 root of positive 13 over 7. Let's move to the little worksheet and see if we can quickly recognize what's happening. So I'm going to do a comparison here with the two problems, 13 and 3. So I'll do the first one. Well, I guess I don't know if the colors are changing. I'll just do the first one. Here's number 13. So if this is a pattern, I begin and end with positive perfect squares. So I've got 2u, and the square root of 25 is 5. The operation in the middle is addition. If in fact this is a perfect square, I'm going to have 2 times 5 is 10. 10 plus 10 is 20. So I'm confident that that was the factor form for this. That would be 2u plus 5 squared. And notice that these are not equations to solve. This is just a little worksheet to help you recognize the pattern when you see it. Let's compare that to number 3 below. Notice it begins and ends with 4 and 25, just like the problem above, but it's going to be the linear term in the middle that does not work. If I multiply 2 times 5, I get 10. The term in the middle should be 10 plus 10. Here it's 16. So that does not generate the pattern that we're looking for. And the next two that I would like to compare on the video would be number 14 to number 12. Notice that they both begin and end with 49 and 9, but their difference would be the term in the middle. So let's see if we can generate this pattern and figure out which one actually is the PST that we're looking for. So the square root of 49 is 7, and we'll put the variable with it. The square root of 9, they have double variables, so I'll just attach the second variable to the term that I'm getting ready to take the square root of. So the square root of the last term is going to be 3b. I notice that both have subtraction, so I just need to test for my middle term. 7 times 3 is 21, so I need the trinomial that has a middle term of 42. So that means that number 12 could be generated by multiplying 7u minus 3b times itself. Notice that number 14's term in the middle is negative 31, and that cannot be generated by adding 21 to itself. Let's see, let me erase this and move up to check out a few other patterns at the top. Let's just look at a few patterns up here and see. It's really simple when the lead coefficient is positive 1. So here, problem like this. The square root of 36 is 6. Square root of t squared is t. My operation in the middle is negative. Negative 6 plus negative 6 is negative 12, so that checks. Let's see, looking at the problem right below it. The square root of 81 is 9. Square root of t squared is t. Operation in the middle is subtraction. 9 plus 9, negative 9 plus negative 9 is negative 18. So that would generate the pattern for that. Let's look at letter S. The square root of 9t squared is 3t. The square root of 4 is 2. Operation in the middle is subtraction. 3t times 2 is 6, or negative 6 in this case. Negative 6 times 2 is negative 12. So it's generating the pattern. And I think that's enough on the video to enable you to at least begin to recognize the pattern and then factor it rather quickly when you see it on a test or quiz.